Hi, my name is Magdalena Dobinda and I am talking to you on behalf of Group 27. Our project is called NSynth, which is our Monophonic Hybrid Analog Digital Synthesizer. We are a four-person group made up of two electrical engineers, Anna Wegener and Sebastian Carrion, and two computer engineers, Devin, Vanzant, and myself, Magdalena. To explain our motivation for our project, we wanted to quickly reiterate exactly what a synthesizer was. And in short, a synthesizer is a musical instrument that you can use to design your own sounds. Analog synthesizers utilize electrical currents to generate sounds, while digital and software synthesizers use binary code, algorithms, and digital signal processing to do the same effect. Aside from the many knobs, ports, and cables that you usually think of when you think of a synthesizer, a lot of them utilize a keyboard that makes it much easier to play these sounds, and as a result, you can physically interact with your sounds across multiple octaves just to see what sounds best. As for our motivation for this project, it firstly implements a lot of challenging core concepts that we have learned throughout our degrees as electrical and computer engineers. It also bridges these concepts together with music theory, computer science, and music production. And while this project exists in different forms, it's very challenging to implement this product in a hybrid form, and as such was our main motivation for picking it as our senior design project. We wanted to bring back the vintage style analog synthesizer and allow people to use it with modern technology. This can be done by creating a MIDI to CV converter, as most modern digital synthesizers utilize MIDI signals. And once we have created the hybrid project, we also wanted to utilize a GUI visualizer that would allow the user to understand in real time how exactly they're manipulating these sounds and also interact with it. Our base goals for this project is divided into software and hardware goals. For the hardware side, we wanted to, at minimum, have the synthesizer generate analog waveforms that could be modulated and modified by the other main elements of the system. The audio signal must also be audible by the end of our demonstration period as well. For the software components, it is essential that we have a working MIDI to CV converter, making the synthesizer MIDI and USB compatible. This can be done and tested by playing MIDI notes on the keyboard and measuring the voltage output at the CV gate. For our advanced goals, we wanted to have a built-in GUI and app interface that can read the MIDI data that is being manipulated in real time and shown in a way that the user can understand how the different parameters are changing. Some of our stretch goals including a module in the synthesizer that would allow the user to connect via Bluetooth, as well as adding advanced features to the GUI previously mentioned. For our requirement specifications, we wanted to make sure that all of our goals were quantifiable in our research phase to allow for clear milestones in this project, and the lines that you see highlighted in yellow are our main features that we'll be focusing on for the demo at the end of the semester. For our VCO, by using two, the versatility of our product doubles, and one can get richer and thicker synthesizer tones by slightly detuning the second oscillator, or known as the sub-oscillator. It can also be detuned an octave or two lower for sub-bass. Regarding this VCO, we wanted to make sure that for the demo, it produces saw, triangle, and square waves, and our VCF has the ability to control cutoff frequency and resonance. For our VCA, we wanted to make sure that when it's used to adjust cutoff frequency through an input-controlled voltage with a distortion less than 5%. For our envelope generator, this will be used to control 4 different stages of sound. These 4 knobs will correspond to attack, decay, sustain, and release. Regarding our MIDI inputs, we wanted to make sure for the demonstration that this is MIDI compliant, meaning that through a MIDI to CV converter, our voltage-controlled analog synthesizer will be able to utilize and manipulate MIDI out signals.
This is our overall block diagram, and it begins with our synth taking input through a MIDI cable that can either be connected to a MIDI keyboard or PC with a USB to MIDI interface. But for our project, we decided to use a MIDI keyboard as the main input source. So first, the MIDI data is sent over a 5-pin DIN cable to the microcontroller, which we've programmed to convert MIDI data into the respective voltages that correspond to the correct notes. The MIDI to CV controller outputs this voltage, known as a control voltage, or CV, to the VCO, which controls the pitch of the oscillator. When a key is pressed, the MIDI to CV controller also outputs a gate signal, either 5 volts high, enabling the 2 envelope generators, or 0 volts low when a key is not pressed. These envelope generators also send a separate control voltage to both the VCF and the VCA to control the cutoff frequency of the filter and amplitude of the amplifier. Then the audio output of the VCOs feed into the VCF to allow the user to control both cutoff frequency and resonance. The VCF then sends this audio signal out into the VCA, where it's then amplified to an audible level for the listener. We also have a goal for a MIDI visualizer built in Java, and we chose Java as it's cross-platform and provides all the built-in libraries that our project requires. Here are our design specifications, so you can see the I/O ports that are going to be on the back of our synthesizer. There's that 5-pin DIN MIDI cable, 120 volts AC in for the wall wart power supply, a speaker output, and aux in if you want to listen with headphones. Here's a rough drawing of what our enclosure is going to look like. So there's the two VCOs with both coarse and fine tune, PWM control and modulation, and their corresponding output levels. So you can control if you want one VCO to be louder than the other. There's also switches at the bottom for wave selection, saw, square, or triangle. The VCF has two knobs for both cutoff frequency and resonance. There's going to be an oscilloscope so that the user can see the audio waveform, and two envelope generators. And those two amount knobs are to control the cutoff frequency of the filter and also the amplitude of the VCA. And this pretty much acts as a master volume. Here's our overall setup. So USB to printer cable from the computer to power the keyboard, 5-pin DIN MIDI cable from the keyboard to the synthesizer, and our wall wart power supply to power the synth. When designing our analog synthesizer enclosure, we had to keep several things in mind: the size of the PCB, clearances around I/O ports, and human interface devices. We had to consider several materials and their cost, longevity, and also their ease of implementation. But we decided to go with an off-the-shelf metal enclosure like one from Hammond Manufacturing. These come with 3D models such that we can ensure the dimensions are sufficient for the size of our PCB, ports, and potentiometers. And we'll use either a Dremel or a drill to make the cutouts big enough for each component. The enclosure also needs to be able to be opened every once in a while to tune the oscillator. So when considering which integrated circuit to use for our VCO, we had to take several factors into account. The most important being price, packaging, waveform outputs, and tracking abilities. But I decided to use the AS3340 due to its popularity in the DIY synthesizer community and also its low cost. I was able to even find the chip for a little under $5, and this made it easier to order spares for our prototyping stage. So now we have extras for when our PCB comes in. The AS3340 has been used in a lot of popular historical synths over the years, produced by Roland, Moog, and Sequential Circuits, and it's popular amongst hobbyists and known as the go-to integrated circuit for VCOs. It has full temperature compensation, making it extremely stable, and has an internal Zener diode to allow it to operate on dual 12-volt supplies for a synth. The VCO uses several unique components to the synth, most importantly being the AS3340, linear potentiometers to control the pitch in PWM, and switches to switch between the different wave types. Polystyrene film capacitors were used on pin 11 for its ideal temperature stability and longevity properties to ensure the VCO stays in tune as long as possible. Other components involved various ceramic capacitors, TLO72s, and various resistors. So the word oscillator itself means something that goes back and forth, and the VCO is the heart of the synthesizer. It uses control voltage to control the pitch at which it oscillates and the user hears as a note. The design we have decided to use for the VCO is based off of the reference design we mentioned earlier, the Sequential Circuits Prophet 1, along with studying the AS3340 connection diagram from the datasheet. Since this is a monophonic synthesizer, we only have one voice per IC, and we have successfully scaled it to the 1 volt per octave Moog standard, so that doubling the frequency will take you up 1 octave on the scale. And after a successful prototyping stage, we have square, saw, and triangle waves, which can be seen here. We continued comparing against the AS chip family. The SSI family didn't offer an envelope generator, so the only one that we had as a contender for comparison was the OnvGen 8C from electricdruid.com. But after comparing the two, the AS3310 continued to win as we favored its exponential response. The envelope generator uses less components than other modules, actually, the most prevalent component being its linear potentiometers. 8 were needed, 4 to control the VCF and 4 to control the VCA. Applying ADSR to the filter allows you to exercise control over the cutoff frequency over time, making the sound more or less bright. And applying ADSR to the amplifier allows you to control the volume out generated by the oscillators. This allows the user to create slow or fast attacks and long or short sustains and releases. The envelope generator is used for controlling the ADSR, which stands for attack, sustain, decay, release of each note. This allows the user to play and hear the synthesizer as if it were a normal piano, giving them the ability to control each note by the amount of force they use when pressing and holding down each note. Attack controls how long it takes for the sound to reach its maximum peak volume during the sound envelope. Decay defines how quickly or slowly the sound takes to decrease from its maximum volume to 0. Sustain sets the volume that the decay will drop to as long as the key is held down. And release takes action once the key is released and controls how long it takes the volume of the sound to drop from the sustain level to 0. And again, for our design, we referenced the Sequential Circuits Profit 1 envelope generator design, along with the AS3310 datasheet connection diagram.
So our voltage-controlled filter. As you know, filters are used to alter the harmonic content of signals. In this case, the signals are coming from the VCO. And the two main parameters we care about for our VCF would be the cutoff and the resonance. The cutoff we known as the cutoff frequency. So in this case, this is the parameter we get to pick the frequencies we want to let pass through. And for the resonance, in other words, which is also known as the Q factor, we, for example, control the damping of the signal. So yeah. So for our VCF IC selection, we had two options, the AS3320 and the SSI 2140. These two ICs had very similar specs, but it made sense to pick the 3320 since it comes in a through-hole IC package, whereas the SSI comes as a surface mount package, which needs to be soldered, which didn't make sense to choose because we prototyped our VCF by breadboarding. So, and so for the VCF parts used, the basic building block of the VCF, what's highlighted in red. This is a configuration that was taken from the datasheet to build a active low-pass filter. One thing to note is also that active low-pass filters are used in audio amplifiers, equalizers, and speaker systems because they direct the lower frequency-based signals to larger bass speakers or to reduce any high-frequency noise or any type of hiss distortion. But aside from that, we see the cutoff frequency stage on blue and the resonance control stage in green. Each one has a pot or potentiometer, which controls each parameter and the output stage. For our VCA, we went with a vintage VCA schematic. We use a OTA, an operational transconductance amplifier, and TL084 op amps. Um, so for our VCA part selection, we chose the LM13700 rather than the other two, the AS3330 and the SSI2162 ICs. This OTA was just free. They had them in the lab. It performs a little bit less than these ICs, but are still fairly on par with what the application needed. For the VCA parts used, we see the envelope generator stage, the single input stage, and the output stage. The envelope generator stage and the input stage, each incoming signal gets combined into the OTA, which is then fed to a current to voltage stage, which is seen at the output stage. So in other words, when it's fed to the current to voltage stage, this output we regard it as a voltage output because it depends on an input current and also by a feedback resistor. So, for example, if we were to change this feedback resistor and increase the resistance of this, we would note that the output voltage would go higher. We'd have a higher voltage. And this works in a similar fashion as an inverting op amp, whereas if you increase the feedback resistor, then you would also see the gain increase. But in this case, it would be the voltage. So for our power supply, we use the wall wart, which takes 120 volts AC from the wall and steps it down to 15 volts AC. We chose as the voltage regulators the LM317 since it's positively polarized to regulate positive voltage, and the LM337, which is negatively polarized to regulate negative voltage. These two have pretty much the same specs, but just opposite. They're just configured for opposite polarities. Here is our schematic for our power supply. Our power supply is a dual linear output power supply, and this power supply is pretty common for any type of audio application, and it's great to use linear regulators since they have a great rejection of AC line ripple, and they tend to be less noisy than SMPS supplies or switch mode power supplies.
One of the biggest parts of our project is going to be the MIDI to CV conversion. MIDI stands for Musical Instrument Digital Interface and is the standard for digitizing musical instruments. In this case, the MIDI device, which is our keyboard, transmits a digital signal, and this signal represents a musical note. Alongside the note, metadata is also sent, and this metadata includes when the note's going to be played, how loud it's going to be played, what the pitch, and etc. Control voltages, or CVs, are basically the opposite of MIDI. They are analog signals, and the CVs can be controlled by knobs that we have on the device, and these knobs will adjust the amount of voltage that's allowed to pass through. For the MIDI to CV conversion, we can see our schematic here. The parts that we use starts with the 5-pin DIN all the way on the far left. Then we have the 1N4148 diode, and then that's connected to the optocoupler. The AT-Tiny85 is the microcontroller that we chose, and that is going to be responsible for actually converting the digital signal to something that can be outputted as analog. It outputs a gate out signal and a CV out signal. This is the block diagram we have just for the MIDI to CV conversion. It basically shows the flow of things. It all starts off with a MIDI controller, generally in the form of a keyboard. At least that's what we're using for this this project. And then this keyboard will produce MIDI out signals. These MIDI out signals are going to go through a MIDI cable to the 5-pin DIN. The 5-pin DIN is basically a female MIDI ports. The signal then travels through the optocoupler, through the MCU, and then will be produced, or will be outputted as gate signals and CV signals for the envelope generator and the VCO. So this is our software flow. The previous diagram was more for our hardware, or it's entirely for our hardware. And in this code, you can see that at the very top, we have an infinite loop that is basically just waiting for any incoming MIDI signals. Once it does detect the MIDI signal, that's when the code starts running. It hits the processing MIDI data part, and then there's two paths it can take, is whether the MIDI message specifies it to be a note on or a note off. If it's a MIDI note on, then it tells the MCU to send the analog signal through the gate of voltage, and this voltage dictates which note is being played. And all these notes lie on the regular musical octave, with each octave being separated by about a volt each. The other side of the coin is the MIDI note off, and obviously it's the opposite of the note on, where it sends a signal telling the gate's output to basically be turned off, therefore killing the sound. We did a lot of comparisons on different MCUs for a project. We looked at about, I think, 6 of them, including Raspberry Pi and the Arduino Nano, which are some of the newer boards, but we decided to go with the AT-Tiny 85 instead. We also have the AT-Mega 328P, which resides on the Arduino Uno, but that's just for programming the AT-Tiny 85. That actually won't be used in the device itself. But we settled with the AT-Tiny 85 because although it looks weak in comparison to the TC40 right next to it, it has enough of what we need. Like, we did take into consideration the capabilities of all the boards that we chose. We looked at the clock speeds and the flash memory and the CPU type, but since we're focusing on a monophonic sound output, that is, like, we're only playing one instrument at a time, we don't need something super powerful, and we can just skip the single board computers such as the Pi and the Nano, and we can opt for the AT-Tiny 85. So like I said in the slide previous, these are the two MCUs we're going to be using. We're mostly going to be relying on the AT-Tiny 85. Again, the AT-Mega 328P on the Arduino Uno is mostly just for programming the AT-Tiny 85. So that way the AT-Tiny 85 is standalone. And the way that we can program it is with a device called USB ASP that hooks up to the computer, and then also to the Arduino Uno. This allows us to basically import Arduino code onto the AT-Tiny 85. A power supply does provide 12-volt output, so we will need a voltage regulator when hooking up the power supply to the rest of the MIDI to CV conversion parts, since the AT-Tiny does run on 3.3 volts to 5 volts. So again, MIDI is a universally recognized digital format, and 5-pin DINs are capable of reading MIDI inputs. So any MIDI-compatible device can interface. There's two main types, and those are MIDI to MIDI and USB to MIDI. We prefer the MIDI to MIDI because, one, it was easier to implement, two, it's cheaper, and three, we only need unidirectional connection because we don't need to send anything back to the keyboard. We're simply outputting for the keyboard only. If we were to have the synthesizer actually output sound on the keyboard, then we would need to opt for the USB to MIDI.
After we finish integrating our project into its hybrid form and can take in digital data, we wanted to take it one step further and integrate a visual GUI to better intensify the experience for the user. Throughout our research phase, we found that Java documentation made room for grabbing MIDI data directly through its APIs with a USB connection. The entire music library that they've integrated will make it much easier for our team to grab the specific data we need from our design to customize the GUI for the user. Our initial budget predictions were far higher than what our team ended up spending so far, as we decided to build our own MIDI to CV converter from scratch rather than buying one, which saved us a lot of money. Most of our hardware remained within budget, and the main issue we had was reordering parts that weren't breadboard mountable or did not work as predicted. The keyboard was our highest purchase so far, and it was necessary to purchase as we couldn't find any to borrow that had a 5-pin MIDI out and in ports, as they're made for mainly USB ports now. We will try to stay within UCF services offered to save on enclosure costs and other unexpected fees. In this chart, you will see our progress so far from the beginning of our senior design journey until now. Throughout the project, we have done a significant amount of research on the best practices and parts to use for a successful project, and our first initiative is nearing an end as almost all prototyping and parts were ordered and tested. Regarding testing and breadboarding, most of our subsystems from our synthesizers are coming together and working appropriately with a lot of trial and error. We're nearing the end of the breadboarding phase and beginning to see the PCB creation come to life. We need to order the PCBs as soon as we can so we can focus on our enclosure process, demoing, and hopefully a few of our stretch goals. Overall, our progress timeline is on track to complete by their deadlines and senior showcase. Thank you so much for your time.